Hello, my dear students. Am I audible now? I believe I am audible. Okay. Fine, 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 fine. So, everyone's here? Good afternoon. क्या हुआ मैं दिख रहा हूं सबको? Yes, I am visible. Fine, 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 fine. So, yes. तो चलिए आज क्लास शुरू करते हैं और किसी को कोई डाउट है तो वो पूछ सकते हैं. सारे के सारे डाउट्स आर एब्सोल्युटली एक्सेप्टेबल. तो आज हमने अपना सेशन शेयर किया है क्या? नहीं किया है. कोई बात नहीं, अभी हम अपना सेशन शेयर कर देंगे. तो आज हम करने वाले हैं फॉर द वेरियस आज सचिन से का सेशन आपका थोड़ा सा लेट चला था आई बिलीव. और आज हम करने वाले हैं आज अ वेरी 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 इंपॉर्टेंट टॉपिक. एंड व्हाट इज दैट वेरी वेरी इंपॉर्टेंट टॉपिक? वी आर गोइंग टू टॉक अबाउट द मॉलिक्यूलर ऑर्बिटल थ्योरी. अब मॉलिक्यूलर ऑर्बिटल थ्योरी के बारे में बहुत सारे स्टूडेंट्स कंफ्यूज होते हैं. द पीपल गेट कंफ्यूज अबाउट द मॉलिक्यूलर ऑर्बिटल थ्योरी, बट दिस इज गोइंग टू बी एन एक्सट्रीमली सिंपल कंसेप्ट एंड एक्सट्रीमली सिंपली वी आर गोइंग टू डू इट. सो रेडी फॉर इट? अपनी कॉपी पेन ले आयो, बुक ले आयो. ठीक है. Okay, so what do we find? Ready? चलो. सो अब आपकी सबकी तकलीफें तो दूर हो गई है ना? अबाउट physics. So now you have all physics, chemistry, botany, and zoology. The bonding and molecular structure we are going to talk about, and NEET Elixir Droppers batch is going to start from 16th of August with physics and chemistry and botany and zoology. So everything is going to be there. And botany is going to be 6:30 to 7:30, chemistry 7:30 to 9, zoology 9 to 10, and physics is going to be decided very soon. And where is my मेरा सेशन कहाँ गया भाई? चलो यहां से नीचे से कर देते हैं. Great. So this is how we can join it and use the code AV Live. So let's get along with something called molecular orbital theory. The molecular orbital theory, MOT. Clear? Now let's see why we need molecular orbital theory. Need for molecular orbital theory. Need for MOT. What is the responsibility? What is the problem in other theories that we need molecular orbital theory? Okay. The very first requirement, very first responsibility, very first need, that why do we need molecular orbital theory? Hybridization does not exist. Hybridized orbitals can be calculated, but they cannot be observed. So that is the first thing, hybridization does not exist. Excuse me. The very first thing. Okay. Second, what's the problem? Hybridization cannot explain breaking of bond. हाइब्रिडाइजेशन बॉन्ड की ब्रेकिंग को एक्सप्लेन नहीं कर सकता. ठीक है. तीसरी बात, hybridization cannot explain paramagnetic behavior of simple molecules like B2 and O2. In fact, ऑक्सीजन का पैरामैग्नेटिक बिहेवियर हाइब्रिडाइजेशन एक्सप्लेन नहीं कर सकता, एंड दैट इज द मेन रीजन व्हाई वी टॉक अबाउट द मॉलिक्यूलर ऑर्बिटल थ्योरी. इज इट क्लियर? Ananya se kaha, monocentric is single atom, polycentric is spread over more than one atom. That is polycentric. Okay. So Prerna Rajput, you are watching the class in your TV. That's great. But I believe the resolution is good enough that you are able to see it in your television. Okay. So that's what we have as the drawback of hybridization. And now we are going to talk about the molecular orbital theory. And before we get along with the molecular orbital theory, let's talk about something called paramagnetic and diamagnetic. We talk about paramagnetic and diamagnetic. So let's talk about this. What is paramagnetism and diamagnetism? So let's talk about what is paramagnetic behavior. Paramagnetic is any species containing unpaired electron is attracted towards magnetic. Okay, this is called paramagnetism. This is paramagnetism. Okay, and then we have something called diamagnetism. Diamagnetism, any species containing all the electrons paired. Species which have all paired electrons are slightly repelled by magnetic field. Now this is termed as diamagnetism. So a species, Dr. Akash Patra says, why O2 being diamagnetic behave like in magnetic? Who said that O2 is diamagnetic? I told you that O2 is paramagnetic. I just told you, Akash, that O2 is paramagnetic. Why do you say this? Why do you say that O2 is diamagnetic? Okay. So the species which have all paired electrons are slightly repelled by the magnetic field, and that is what we call as diamagnetism. Clear? Now we are going to talk about the molecular orbital theory. Molecular orbital theory can be done in two ways. One, we can consider it through mathematics. खूब सारा mathematics लगा के हम molecular orbital theory कर सकते हैं. And the other way of doing molecular orbital theory is by simple concept and simple logic. So we are going to do molecular orbital theory by simple concept and simple logic. We are not going to talk about very difficult mathematics doing molecular orbital theory. So let's do it by simple method. Let's talk about a very simple molecule. Let's talk about the hydrogen molecule. Okay, fine. ध्यान से समझना, ध्यान से देखना, कोई भी डाउट होता है इमीडिएटली पूछ लेना. We have the hydrogen molecule. What is hydrogen molecule? We have one atom of hydrogen. Okay, and we have another atom of hydrogen. These are the two atoms of hydrogen. Clear? Here we have the nucleus. Here we have the nucleus. The two hydrogen atom have one electron each. So here it's going to have one electron, and this is also going to have one electron. Now you may consider electron as a particle, you may consider electron as a wave. Here does not make a difference because the logic which we are talking about is going to be applicable to the wave as well as particle. So that is not a confusion. Yes, this is chemistry lecture, beta. Is it clear? So that is what we have as the hydrogen molecule. Any confusions? Now what I consider is that I take both the nuclei. दोनों हाइड्रोजन के न्यूक्लियस ले लेते हैं. I place the two nuclei here. Okay. Now these two nuclei are going to repel each other. Now let's place an electron in between these two nuclei. I just try to put an electron. Okay. Where will this electron go? Obviously, electron is going to try to be at the position which is going to be most stable, and it is going to have the maximum attractive force with the nucleus. There I am going to put the electron. So that electron is going to have a tendency to occupy the space between the nucleus. Okay. So the electron will have a tendency to occupy the place between the nucleus. Electron placed between the nucleus is attracted to two nuclei. So it will have a lower energy. Okay, so it is going to have a lower energy as compared to the electrons in the separated atoms. So what we can say is, now remember, the region in which an electron exists, the region in which the electron exists is termed orbital. Okay. Orbital around a single nucleus is atomic orbital. Okay. Orbital spread over two or more nuclei is molecular orbital. Okay, so this one is a molecular orbital. Fine. So here it is a molecular orbital. कोई दिक्कत किसी को? Anybody has a problem here? Okay. Now, if we talk about this particular orbital, this electron present between the two nuclei is going to act like a glue. ये दोनों के बीच में गोंद की तरह act करेगा, and it is going to attract the two nuclei towards themselves. So it is going to act like a glue between the two nuclei. It is going to try to make a bond between the two nuclei. And since it is trying to create a bond between the two nuclei, it is a bonding molecular orbital. Clear? So this is a bonding molecular orbital. Clear? If we talk about the energy levels, let us say this is the energy. This is the energy of one atom. Let's say this is the energy of H1, or rather I'm not sure should write it here. Let's say A कर देते हैं, HA कर देते हैं. Okay. Now, this is the energy level of another hydrogen atom, let's say HB. This will be the energy of the molecular bonding orbital. So, bonding molecular orbital is going to have lower energy. The electron placed here is going to be more stable. It is going to make the system's energy less. It is going to make the system more stable. Clear? Fine. Now, there is something called, okay, we are going to talk about that later. Okay, fine. So, we have just put the bonding molecular orbital. Let's put one more electron here. Now, if I put another electron, that electron is going to occupy this particular position here. Each orbital has a capacity to accommodate two electrons. So, two electrons can go into the bonding molecular orbital. So, here the another electron is going to occupy this particular position. Two electrons are occupying the bonding molecular orbital. Now, the problem arises when we talk about the third electron. If I try to put the third electron, the electron is not going to occupy any of these positions because this position is already occupied. Only two electrons can exist in an orbital. If I want to put the third electron, it can occupy a region somewhat here, or it can occupy the region somewhat here. Clear? Now, if I put the electron in this region or this region, whatever region these two are, yellow regions are, the electron gets attraction of only half the nucleus. Since it is getting lesser attraction, it gets the attraction of only half the nucleus, its energy is going to be high. Okay. It will have a higher energy. Okay. It will have a higher energy. It is going to make the system unstable. Clear? Now, if it is going to make it unstable, it is going to become anti-bonding orbital. So this is what we call as the anti-bonding. Again, it is a molecular orbital. Dr. Akash, it's not just away from the nuclei. It is not away. The distance is not high. The only thing is its positioning. Its positioning is to the other side of the nuclei, where it is getting the attraction of only half the nucleus. And that is why its energy is going to be more than the energy of the individual unoverlapped orbitals. Now, this becomes anti-bonding molecular orbital. Is this clear? It has a higher energy as compared to the orbitals which are mixing to form the molecular orbital. Clear? So that's what we have as bonding and anti-bonding molecular orbitals. They are very simple to understand. Of course, these are the regions where the electron can exist. Fine. So that's what we have as bonding. That's what we have as anti-bonding molecular orbital. And these anti-bonding molecular orbitals, if the electron goes in, it becomes unstable as compared to the separated atom. Please remember here it is not an absolute value. Here we are just comparing them as compared to the separated atoms. So if we put the electron in the anti-bonding orbital, it's going to increase the energy as compared to the separated atoms. Akash Patwa, the maximum amount of orbitals in a molecule is infinite. Clear? The maximum amount number of orbital is infinite. The important thing is how many orbitals are going to be occupied. So we are not talking about the total number of molecular orbitals present. We are only talking about how many orbitals are actually occupied. That is what is important. Is this clear? So the electron gets attraction of only half the nucleus. It'll have a higher energy. It is going to be unstable. This is going to be an antibonding molecular orbital. Okay. And now we have something called the bond order. Bond order. What is the meaning of bond order? Prenam, antibonding molecular orbital is the orbital which has a higher energy as compared to the separated orbitals. Clear? So this one is a higher energy. This one is a lower energy. So bonding molecular orbital, they make the system stable, and the antibonding molecular orbitals make the system unstable. Is this clear? And do you remember we have the session at 8 o'clock? Yes, we are talking about the bond order. Bond order is number of bonding electrons minus number of anti-bonding electrons divided by, as in the Lewis dot structure, 2. So we are going to talk about the electron, the bond order as divided by 2. Clear? Okay, so that's what we have as bonding and anti-bonding electrons. Now we are going to talk about the molecular orbital theory. Okay, what is exactly molecular orbital theory? What does it entitle and what does it mean? It says that the atomic orbitals of different atoms having similar energy overlap to form a set of molecular orbitals. Clear? Is that clear? So that is what we have as molecular orbitals. Now, once we have talked about the set of molecular orbitals, here we talk about what exactly it means. What exactly is the meaning of how many orbitals are going to be formed? The number of molecular orbitals formed is the same as number of atomic orbitals mixing. Okay? The number of molecular orbitals formed is the same as the number of atomic orbitals mixing. If two atomic orbitals are mixing, two molecular orbitals will be formed. If three atomic orbitals are mixing, three molecular orbitals will be formed. So the number of molecular orbitals formed is the same as the number of atomic orbitals mixing. Okay. Now, the filling of orbitals is according to Aufbau principle. Okay. So the number of orbitals, the electrons are going to be filled in the orbital according to the Aufbau principle. That is the same thing. The very three principle, that is what we have. Lowest energy orbital filled first. Okay. The lowest energy orbital filled first. Second, no two electrons, or at the we should say maximum two electrons per orbital with opposite spin. Okay, maximum two electrons per orbital with opposite spin. And C is that for same energy orbitals. Same energy orbitals are called degenerate orbitals. Are first filled singly. Are first filled singly before electron pairing. Now, these are three Aufbau principles. Of course, the third principle happens to be what we call as Hund's rule of maximum spin multiplicity. The second is called the Pauli's exclusion principle. So these principles are again being used in creating the arrangement. Is this clear? Okay, I believe you all have attempted the paper. Any confusions? So these are the steps in filling of electrons. Now, here we can say that the atomic orbitals could be of any atoms. You could have any number of atoms, you can have any number of orbitals, we can have any energy, we can have any so many combinations which are possible. Okay, that's good अनन्या, अगर आपको समझ में आ रहा तो बहुत अच्छी बात है. Okay, so they are first filled singly before electron pairing. Okay. Now, there are infinite possibilities of molecular orbital formation. Okay, there are infinite possibilities for molecular orbital formation. So, as is very, very clear, we cannot talk about all the possibilities. We can talk only about a few possibilities. Clear? So, what is there in our course? Our course has a very limited arrangement, very limited possibilities. And what are those limited possibilities? These are homonuclear. Homonuclear. Homonuclear means that we have only identical nuclei. Identical nuclei. Homonuclear. Diatomic. Diatomic means only two atoms. Homonuclear diatomic molecules. That is, we are not going to talk about O3, we are only going to talk about O2 because O3 becomes triatomic. So we are going to talk only about homonuclear diatomic molecules up to atomic number 10. Only we are going to talk about homonuclear diatomic molecules up to atomic number 10, not beyond that. Okay. Now, here we get only a few combinations. So actually speaking, we have only three types of orbital, three different orbitals which can overlap under this condition. We can have a combination of 1s and 1s. We can have a combination of 2s and 2s. We can have a combination of 2p with 2p. 2p and 2p can have two kind of combination. We can have the lateral overlap and the axial overlap. Axial overlap, and we can have lateral or parallel overlap. Okay, these are the overlaps which are possible. Axial overlap is possible and lateral or the parallel overlap is possible. Okay, so now let's see these overlaps and how they are formed. Anybody has to ask anything till this point? Okay, let's talk about the combination of 1s with 1s or 2s with 2s. Important thing is s orbitals are spherical. Whether we talk about the orbital overlap of 1s with 1s or we talk about orbital overlap of 2s with 2s, it's going to be the same. Clear? So let's talk about the orbital overlap of 1s with 1s. So here we have the 1s orbital and here we have the 1s orbital. So when they are going to overlap, there are two possibilities. There are two possible regions of overlap. Here we have this line. Now this line passing through the two nuclei is termed internuclear axis. This is what we term as the internuclear axis. Fine. So here we have one nucleus, here we have another nucleus, and then we have the two different regions. What are the two different regions? One region is this, the region between the two nuclei. Okay, this is the region between the nuclei. Clear? Now, in this region, electron has lower energy. The electron has a lower energy in this region. Clear? So now when the electron has a lower energy in this region, what we are going to talk about, this region is going to be created in this manner. It is going to be written like this. Okay? And then we could have this region. This region is written in this manner. It's made like this. Yeah? Or rather, I should not make like this. I would make like this. This is the bonding region. This is the anti-bonding region. Clear? Now let's have another definition. Let's talk about the sigma and pi bonds, or you may call it orbitals. Sigma and pi orbitals. So let's talk about the definition of the sigma orbital first. The orbitals in which the maximum electron density, the orbitals in which the maximum electron density is on the internuclear axis are termed sigma orbitals and the bonds formed by them are are sigma. Is it clear? So that is what we have as the sigma bonds. Okay. And then we have the pi bonds. Pi bonds are pi orbitals. The orbitals in which the electron density is above and below the molecular plane, in which the electron density is above and below the molecular plane and internuclear axis is in the nodal region. Okay, internuclear axis is in the nodal region. अभी तक जिसने भी लाइक नहीं किया जल्दी से लाइक कर दो. इन द नोडल रीजन. अब इसके बाद हमारे पास एक और डेफिनेशन आती है नोड. द रीजन वेयर probability of finding electrons is the that is termed as the node. Clear? So here we find that the molecular axis in the nodal region, that is internuclear axis पर pi bond का इलेक्ट्रॉन होने के चांसेस सबसे कम होते हैं. Okay, the bonds formed by them are termed pi. Clear? So we have just understood what is the meaning of the sigma bond. That's what's the meaning of the pi bonds. Clear? So here, these are sigma bonds. Because here, the internuclear axis is the one which has the maximum electron density. Yeah. Now further, anti-bonding orbitals are represented by putting a star on the symbol. That is what we have, a sigma star or maybe pi star. Electron is not least in pi bond. Electron is least on the internuclear axis in the pi bond. Electron is not least in pi bond. Who said that electron is less? Whatever electrons are present, those are going to be present. So we are not going to talk about less or more electrons. Is it clear, Ananya? Is it clear? Okay. So here what we find is that this is going to be sigma, and here we are going to put a star here. This is an anti-bonding orbital. We call it a sigma star molecular orbital. or sigma star orbital, simply as that. Sigma orbital, sigma star orbital, that is what we say. Now we can write it as sigma 1s or we can write it as sigma 2s depending on which orbital are being used. Similarly, we are going to get sigma star 1s and we are going to get sigma star 2s. So that is what we have as the bonding and the anti-bonding molecular orbitals. And we have talked about what is sigma and the pi molecular orbitals. So here we have talked about the overlap of the 1s with 1s orbital. This is 1s with 1s orbital or 2s with 2s orbital getting the bonding and the anti-bonding. Now, many a times we put some sign in the molecular orbital, something like we put a plus sign here. We put a plus and the minus sign here. Okay. These plus and the plus minus sign in the molecular orbitals represent the sign of wave function in that region. Is that clear? Anybody who has not liked the session, go ahead and like the session. Fine. Please remember, it has nothing to do with charge or probability. Is this clear? It has absolutely nothing to do with charge or probability. Clear? So that is what we have as the plus or the minus. Now, one more thing. Let's talk about the symmetric and unsymmetric orbitals. If I take the line point at the center and I move in a certain direction, okay. Now what I do is I move from the center in the opposite direction. If I get the same environment, I would call the orbital is symmetric. Okay. Okay. symmetric and unsymmetric orbitals. Okay. On moving from the center to in a certain direction, we find an environment. Okay. If on moving from center in opposite direction to the same distance, if same environment is observed, the orbital is symmetric. Else it is unsymmetric. क्लियर? हंसी कैसे पढ़ो बेटा, क्या लिखा हुआ है यहां पे? अभी मैं करके दिखाता हूं. सी हियर आई मूव इन अ सर्टेन डायरेक्शन. यहां से हमारे पास ये है. आई मूव इन दिस डायरेक्शन. When I move in this direction, I get a negative sign. What I do is I move in this direction, exactly opposite to the direction which I moved. And here I get the positive part. Here I get the negative. Since these are the different sign, I would say this is unsymmetric. Is it clear, Hansika? And let's talk about this one. Here I move from the center to this direction. It is positive, no problems. Then I move in this direction, again it is positive. So I get the same environment in both the direction when I move to the certain same distance. Is it clear? So this one is symmetric. So what we can say is sigma bonding orbitals are symmetric while sigma anti-bonding is unsymmetric. So sigma bonding is symmetric. Okay. Sigma star, that is sigma anti-bonding, is unsymmetric. Clear? Clear. Now let's talk about the overlap of the p orbital. So let's talk about the overlap of 2p with 2p. Now first of all, we talk about the axial or the linear overlap. Okay. Axial overlap. Now when we talk about the axial overlap of 2p and 2p, Here we have the p orbital. This one is one axis. This one is the axis of another atom. This is the internuclear axis. Now we create the orbitals, the p orbitals that we talk about. This is one p orbital. This is another p orbital. Now, since we are talking about homonuclear diatomic molecules, these p orbitals have exactly the same energy. So maybe this is plus, this is plus, this is minus, and they overlap. So this is going to be certain region. This is going to be a region. Okay. There is going to be a region between the nuclei, and there is going to be a region away from the nuclei or behind the nuclei. Yeah, antibonding sigma orbital is unsymmetric orbital. Unsymmetric, asymmetric nahi. So when we create the orbitals, this part is going to be created in this manner. Now this is sigma 2p bonding. Now what we mostly consider is this is the internuclear axis. Considering internuclear axis, Z axis. So we have considered Z axis to be the internuclear axis. It's not a necessity. It could be P, it could be X, could be Y, could be Z. So NCRT has a question in which it says that considering the internuclear axis to be the X axis. Okay. If it is Z axis, then in that case, this would be the PZ orbital. This would be the PZ orbital. The PZ and PZ orbital are going to overlap on the Z axis to give the sigma 2pz bonding orbital. Anyone has any kind of confusions here? And then we have the anti-bonding orbitals. How do we get the anti-bonding orbitals? Let's make the axis first. This is the internuclear axis. And here we get it, anti-bonding orbitals. Okay. Here we are going to get a plus here, minus here, minus here. Here it's going to be plus, minus, plus, minus. Now this is going to be symmetric. This one is going to be unsymmetric. Okay. This is sigma star 2pz. Please remember it is Z because we have considered the internuclear axis to be the Z axis. That is why it is the Z axis. Anyone has any confusions with that? Okay then. Let's talk about the parallel overlap. Let's talk about the parallel overlap. Parallel overlap or lateral overlap. Now here, what we can see in the parallel or the lateral overlap is if we consider the internuclear axis to be Z, then the lateral overlap, the orbital could be Px or Py. So this could be Px with Px or Py with Py. Is this clear? Now, when they overlap with each other, there would be again two regions formed. One region in between the nuclei and another region which is not in between the nuclei. So these are the two regions which are going to be formed. And let's make these regions. One region is formed here. Okay. Now, as you can very well see that this internuclear axis is in the part of node. So it's a nodal region. So quite obviously, this is a pi orbital. This is the pi 2px or pi 2py. It could be any of these two. And here we are going to have a positive and here we are going to have negative, and this is unsymmetric. So Ansika, that's what I said, it's unsymmetric. क्या सेम है? यहां से अगर हम जाएंगे तो ये यहां पर हमारे पास पॉजिटिव है, ठीक है? यहां पे अगर हम जाएंगे तो दिस इज गोइंग टू बी नेगेटिव. सो हाउ इज इट सेम? इट इज डिफरेंट. पेन तो कहा ही नहीं सेम बेटा. आपने सेम कहां से सुन लिया? Is this clear? So this is symmetric and the unsymmetric. So this part is unsymmetric. This is sigma 2px or sigma 2py bonding molecular orbital. And then we can have the anti-bonding molecular orbital. Now, if we discuss about the anti-bonding molecular orbital, we are going to have the four regions. One region is going to be this. Another region is this. Another region is this. And another region is this. Okay. Now here we are going to have positive, negative, positive, negative. So if I start from the center in this direction, this is going to be negative. And if I start in this direction, this again is negative. Okay. So this one is symmetric. So this is pi star 2px or pi star 2py. The antibonding molecular orbital, antibonding pi molecular orbital are symmetric. Okay? Anybody has to ask anything here? Now just remember, there are two nodes in the pi antibonding. This one is a node, okay, and this one also is a node. So there are two nodes in pi star 2p orbital perpendicular to each other. Any doubts? Is this clear? So that's what we have as the node, and that's what we have as the parallel and the axial overlap of the p orbitals. Clear? So once we have talked about these orbitals, Hansika, the star talks about the anti-bonding orbital. It has nothing to do with symmetric or unsymmetric. Is it clear? Star talks about anti-bonding. Clear? So pi star means anti-bonding pi orbital, which happens to be symmetric. Sigma star is anti-bonding sigma orbital, which happens to be unsymmetric. Is this clear? So star has nothing to do with symmetric or unsymmetric. Is it clear? Now, so here we have talked about the orbitals. Now we talk about the energy diagram. Energy diagram. When we talk about the energy diagram, there is a very peculiar thing. एक छोटी सी बात देखो. We have sigma 2s orbital. and we have the sigma 2p orbital. When we talk about the sigma 2s orbital, sigma 2s orbital has this region. Hmm. Sigma 2s has this region. Okay. And when we talk about the sigma 2p, sigma 2p has this region. Okay. Now, as you can very well see, sigma 2s and sigma 2p have same probability region. Okay. Is it clear? Sigma 2s and sigma 2p have same probability region, or rather, I should not say same, I should say similar. Not exactly same. Okay. Now, if they have similar probability region, then in that case, if they have similar energy, they also can overlap. Okay. So, if they have similar energy, they also can overlap. Fine. Now, one thing you need to understand, moving across the period, that is left to right. And when we talk about left to right, it's going to be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Energy gap between Ns and Np orbital increases, making overlap of sigma 2s and sigma 2p difficult. Okay. When we talk about lithium, the energy gap is somewhat around 200 kilojoules per mole. When we talk about fluorine, this energy gap becomes similar to 2500 kilojoules per mole. So as we are moving across the period, Ns and Np energy gap is increasing. So overlap becomes more difficult. Is this clear? Now, here what we get is, this is going to be the 2p orbital, or sigma 2p orbital, I should say. Sigma 2p orbital. And here is sigma 2s orbital. Okay. They mix with each other, and what we get is we get two new orbitals. One orbital is higher than both the orbital and another orbital is lower than both the orbital. So the energy of sigma 2p actually rises and energy of sigma 2s actually decreases. And this is termed as sp mixing. Okay. sp mixing leads to an increase in energy of sigma 2p and decrease in energy of sigma 2s. Anyone has to ask anything here? Anyone has to ask anything here? Now, अब ध्यान से सुनना बिना किसी कंफ्यूजन के बहुत आराम से बहुत ध्यान से सुन लेना जो मैं कह रहा हूं ओके ओके ध्यान से सुनना सिग्मा सिग्मा 2p z should have lower energy than pi 2px and pi 2py as overlap is more efficient. Is this clear? हाँ ये सिर्फ लाइटी पे लाइव स्ट्रीम हो रहा है बेटा और कहीं पर नहीं हो रहा और कहां पे होना चाहिए ओके सो दिस ओवरलैप इज मोर एफिशिएंट बट इन केस ऑफ lithium beryllium boron carbon nitrogen due to sp mixing the energy of sigma 2pz becomes more than pi 2px and pi 2py. Okay, just check it out. Is this clear? This is due to sp mixing. Otherwise, that the sigma 2px and sigma 2py, the pi 2px and pi 2py should have a higher energy than sigma 2pz. But what happens is sigma 2pz actually happens to be having a higher energy as compared to the pi 2px and pi 2py. Is this clear? Now, let's talk about the energy level diagram. Energy level diagrams. Here we have one orbital. Here's another orbital. Here is another orbital. Here is another orbital. Here we have the 2p orbitals. Here we have another 2p orbitals. Okay. This is 1s. This is 2s. These are 2p. Is this clear? So 1s, there would be a lower energy orbital. That is sigma 1s. There will be a higher energy orbital. This is sigma star 1s. Is that clear? Now, sigma 1s and sigma star 1s. Here it would be formed. Then we have 2s. This is sigma 2s. This is sigma star 2s. Clear? Okay. Then I have here. Now, when I'm talking about the diagram up to N2 with SP mixing, I'm talking about up to N2 with SP mixing. So here we are going to get the two of the pi orbitals, that is pi 2px and pi 2py. And here it would be sigma orbital. This is sigma 2pz. Here above it is going to be again pi to px, and this is pi star to px. Here would be pi star to py, and this is sigma star to pz. Is this clear? Clear? We can actually see the order here. The order is sigma 1s, then we have sigma star 1s, then we have sigma 2s, then we have sigma star 2s, and then we have pi 2px, pi 2py. We have then sigma 2pz, then we have pi star 2px, pi star 2py, and sigma star 2pz. Whether you remember the diagram or you remember this order, your wish. Whichever you feel like comfortable, you have to remember one of the two things. दोनों याद कर लो, बहुत अच्छी बात है. एक याद कर लोगे, ठीक है, कोई बात नहीं, चल जाएगा काम. Anybody who has not liked the session, go ahead and like it. Is it clear? So that is up to nitrogen. Now let us talk about the other one. Fine. So we have here the energy diagram without sp mixing. That is for O2, F2, Ne2. Clear? Any confusions? So when we talk about O2, F2, Ne2, एक काम करते हैं, आज स्पेशल क्लास लगा लेते हैं. Let's have a special class today itself after the discussion. Let's say at 10 o'clock, 10 p.m. Special class लगा लें. And there we are going to do the molecular orbital diagrams of various elements. कर लें? Now here when we place the element, the bond, here it's going to be, this is sigma 2pz. Here would be pi 2px, pi 2py. Here it is, pi star 2px, pi star 2py. And here is sigma star 2pz. Any confusions? So here the order which we find is बहुत simple सा order है हमारे पास sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, and sigma star 2pz. So this is the order of energy when we talk about oxygen, fluorine, and neon. So that is what we have as molecular orbital diagram for these elements. Any kind of confusions here? Any problems here? ठीक है? So that is what we have as any energy diagram without sp mixing. So we are going to talk about these elements, these molecular orbital diagrams in the next class, that is the special class at 10 o'clock today. Is it clear? So I'll just create that class and share it with you. So be in the class, special class at 10 p.m. कोई और क्लास तो नहीं है उस समय? अगर हो भी तो क्या कर सकते हैं? Okay? So you have Botany with Swati Batra ma'am at 2 o'clock, Zoology with Dr. Sachin Kapur at 3 o'clock, and Chemistry with me at 4 p.m. Okay? Join our Telegram channel for YouTube classes PDFs, t.me/NEET Elixir. Okay? This is what we have as the course. Join with us. Unacademy.com/Anoop Vashishtha. Follow me and subscribe to NEET Elixir by Unacademy for the best live classes. Thank you. Bye bye. मिलते हैं आपसे at 8 p.m. and then at 10 p.m. Bye bye.